them back on a stack. In Swift version 5, they discovered that a constant pool is actually a relatively good idea. And so they introduced constant pools and objects that could have methods. In Swift version 6, they actually then discovered that if you have objects, it would be really interesting to have initialization code. So they introduced a new tag type for that. They also introduced checking of types, which they now had. So they actually have, in Swift version 6, they actually start to have numeric data types and stuff. In 7, the OOP functionality was enhanced, so the objects actually could have inheritance and extension, and they introduced exceptions because they're useful, and they introduced explicit typecasting. Version 8 never happened, and version 9 then introduced the AVM2 into the format which we're looking at right now, which is Swift version 10. Keep in mind that's all still supported. So where would we actually look for code in a Flash file? We talked about the tag types. There is a tag type called doAction that usually carries most of the AVM1 code. DoInit action is the tag type I mentioned for initialization code. But there is also other strange cases, like the define button 2 tag, which contains a button record 2 structure that can carry additional button condition actions, which then carry AVM1 code. So you have a data structure with a data structure with a data structure with a little bit of code. The same also holds true for place object 2 and place object 3 tags. The interesting thing here is this code is actually triggered depending on how it clips. So you have 2 objects and they overlap each other a little bit. That's called clipping. So part of one of the object is cut away. And if that happens, the code that is actually attached to that object is executed. I would really love to know what type of drugs they had. The interesting thing is that many tools that we looked at, also many security tools, actually will only look at do action and maybe do init action for code. They will never discover code that is connected to shapes. The code itself is a variable length instruction set. There is either 1 byte instructions for simple stack operations like add, subtract, not, stuff like that, or n byte instructions with a 16-bit length field. The branches are the branch targets are byte offsets. They're assigned 16-bit offsets into the current code block or wherever. Function declarations, and this is really interesting. So function declarations are actually a bytecode. So in every sane executable format, you have an area that says this is my functions and this is where they start and where they end. In AVM1, you actually have an opcode that says, if I'm executed, everything past me, the next n or whatever bytes behind me, is going to be considered a function. Usually you would put something like that in a file format specification. So my assumption is actually the guy who was responsible for the file format specification was somewhere like on mushrooms, and then the guy who actually wrote the AVM1 stuff had to figure out something for himself. The function declarations also can be nested, or they can be anonymous functions that are executed right after their definition. When they introduced try-catch finally for exception handling, they at least stayed with their initial approach with functions and implemented an opcode, again, that will, when executed, will define try-catch finally blocks. Which means we're running into a lot of weaknesses in this design. First of all, the byte offset branches allow you to jump in the middle of an instruction. Many people that have reversed x86 code that was obfuscated know this typical trick that you jump in the middle of an instruction and then the byte stream gets interpreted differently. This can be done in Flash as well. But you can also jump outside of the code block. You can, for example, jump into an MP3. That's no problem. and it will actually jump into the MP3 and try to execute code there. The signed 16-bit branch offset also prevents large branches, obviously, because you can only jump over 32K. So I was trying to figure out how Adobe actually implements that. So I took the official Flash CS4 developer environment and wrote a very long if statement, an if statement with a very large body, and compiled it. And the compiler actually emits invalid code. So when you execute that, it will actually jump as far as it can, and then everything that was in the if body below that will still get executed. The instruction length field allows hiding of additional data. Obviously, you can set a longer field than you actually need for the instruction, and then hide some data there. And there's argument arrays that you can do the same thing with. The order of code execution is extremely non-deterministic. It depends on the order of the tags and their type, on references, on some conditions to execute, like clipping, and on the visibility of objects. It's pretty weird. So what we do in a code verification, we just check all those properties. Instruction length, the number of arguments that the instruction needs, the declared instruction length, is it completely used? Does the code flow remain within the code block? Does it jump to an instruction that is actually defined, or does it jump into an instruction? Are all the addresses that are coming out of function declarations and in try-catch finally blocks actual instructions? If we do all that correctly, and I believe we do, then we end up with a nice and well-formed Flash file. And this Flash file can actually then be used to counter functional attacks that use Flash functionality instead of trying to exploit the player. Static analysis will provably not be able to determine for any given code what it actually does. That's a problem that we run into in informatics all the time. We considered emulating the code execution, but that will actually cause state discrepancies between your emulation and the actual Flash player. And that would mean that you're making wrong decisions on the functionality of the Flash code. So that's really not an option. So what we do is we do the same thing that you would do in dynamic analysis. In dynamic analysis, for example, let's say you're debugging a Windows binary or something, you will set a breakpoint right at the point in code where the function is executed, like create file. And then you will examine the arguments that are either on the stack or in registers, excuse me, for what is actually in them. Because at that point, whatever obfuscation and strange stuff might have happened before, at that point where the actual execution of the function happens, the arguments must be in place. So what we do is the same thing with Flash. The problem is we're not there when the Flash player actually executes the code. So we can't set a breakpoint within the Flash player. But what we can do is we can actually patch the Flash code in order to perform the checks that we are interested in. How does that look like? Here's an example. Action get URL2. That's again the second attempt to get the operation get URL right. Is the most widely used function or bytecode to actually forward the browser to another URL. When we handle the Flash file, we know where it came from, so we can actually introduce a more strict same origin policy test than the Flash player will actually do. And this is how that looks like. Here's a code flow graph of an original file. And in the block with the ID 31, you see that there is an action get URL, which gets some arguments. In this case, it's constants, but it could be anything. It could be somewhat pre-computed that we couldn't determine up front. So what we can do is we just introduce another two blocks that will actually do a string comparison on the URL that we got the Flash file from. In this case, it's google.com. And if those equal, then we do execute the get URL to. And if not, we just clean up the stack and go on. So nothing happened. This gets more interesting when you try to capture arguments of object methods. I'm not going into all the detail of those code blocks here, but essentially what AVM1 usually does to call a method on an object is first loading the variable by name, and then actually pushing the method name and then calling the method. So you need the code over there to actually figure out if the respective method of a object is called. It gets even worse. If you decide to not have that call happening, this is all the code you need to clean up the stack of the stack machine when you didn't actually execute the function or the method of the object. And you see that this is quite a lot of code. And when you put that into every place where a method of an object is called, you get quite some inflation. That's what you see here. On the left side, the one that's completely blue is the complete code flow graph of the Gnida malware example. On the right-hand side, you see the same code flow graph, and with the little red thingies, that's the basic blocks that we introduced. And you can easily see that we have quite some code inflation here, approximately 250% of the original code. However, every single method call and every single call to an instruction that has anything to do with forwarding your browser to a new URL is actually covered now. So the code is secure, but it's, in my eyes, it's a little bit too big. So what we do to prevent patches on places where we can actually prove that the argument is a constant that fulfills a certain requirement that we have, we can determine those things using backtracing of the virtual machine stack in the code flow. So we build a code flow graph. If we find an instruction that interests us, we do backtracing and try to figure out what the state of the stack is at any given point. The problem is we always need code flow graphs, even if it's a load from the constant pool, because brilliantly enough, the defined constant pool is also an instruction. So within the instruction stream, you can totally overwrite your constant pool. And so we actually have to know in what the code flow is in order to figure out which constant pool is currently used. The goal for the higher level verification model is that we can actually say, like, for an object, for a method, the second or third argument, does it fulfill the following requirement, which is usually a string comparison. So the way we implement that right now is we have our own virtual machine, stack machine. There's actually two. Which gets executed, and it has instructions that are of very small granularity, like get the third argument or argument number n of this instruction, and it will try using static analysis to get to that point to figure out that argument. If it somewhat fails in the execution, so it runs into an undecidable situation regarding the stack state, it stops execution. And we run the same virtual machine again in a different mode where it doesn't actually do static analysis, but actually emits the AVM1 code that will do the same functionality. In this way, we can actually keep the individual functions very small, and we can ensure that the static analysis step and the AVM1 code that we emit are functionally equal, because otherwise we run into situations where those two diverge, and then we can get owned. Very recently, we introduced AVM2 support, the second Adobe virtual machine, so the tool that we released today actually does support both